So for this session, we have João, Pedro, Costa, who's going to be leading the discussion session on QSSEP.
Okay, thanks. So I will try to introduce QSSEP to those of you who don't know about QSSEP, to relate it to classical macroscopic fluctuation theory, specifically of SEP, and maybe try to convince you why it should be a good model to look at the quantum version of macroscopic fluctuation theory. So, okay, I'm going to start by writing down the model. So essentially, QSSEP's Hamiltonian looks like this. So over n, or I'm going L minus 1 over L sides, so something. Okay, where essentially you have noisy hopping. So these are like E2 variables. So essentially this means that if you take the average of these at time t and at time t prime, then this is a Dirac delta in time and delta in space. Yes. Because, yes, there should be a dt here. No, because dw like is the dw squared is equal, the average of dw squared is equal to dt. So the dt is sort of here, if you want. It's like in a stochastic differential equation, you write something like this. So okay, some f dt plus some g dw. And okay, here we don't have these, essentially. You have these. Okay. Okay, I will also consider, I mean, you can write this model on a circle, so periodic boundary conditions, but I will consider open boundary conditions, that there are two reservoirs on the edges of the system that can pump particles into the system at the rate alpha 0 or remove them, and the same here. Okay, okay, I'll do the other way around. Okay, so I mean, in quantum mechanics, I mean, I would write this as like a Lindblad operator. Okay, so why do we want dw here? Because like this, you get diffusion. If you had like constant hopping rates, then you would have ballistic transport on this type of setup, and we want diffusion eventually. And okay, and to sort of show you that you get diffusion, if you take the average of these, so you write your density matrix times t plus dt, and you take average over this noise. What you get is essentially SEP. So you will get some. Yeah, there should be an average here as well. And okay, you get SEP. So essentially, these will. I mean, if you need to expand these up to second order, and this is the same because this is like E2 calculus. You need. There should be a bar here. You need to to dWs and you get the dt. So you need to expand that up to second order. And eventually you get some Lindblad equation from this that I'm going to write simply as these. Okay, where sigma is either plus or minus, meaning jumps to the right or jumps to the left. And okay, these would be something like this, plus 1 Cj, and these would be something like this. Why is this step? Because if you start with a density matrix that is diagonal, so something of this sort, that lives only here, and is 0 everywhere else, your dynamics will keep you on the diagonal, and essentially it will be exactly the same evolution as you have for SEP. So this would be your probability vector in SEP. And so since SEP is diffusive, this model should be diffusive. Okay, so now I would like to maybe give you sort of origin or motivation for this model. So this model appeared from essentially in the beginning, from studying a different model, which is essentially this tight binding model. So but where the noise, and now here it's real noise, so there you have complex noise, lives in, okay, the noise is coupled to your number operator. And you have a factor of kappa here, the root of gamma. Okay, like that one, dw square is equal to dt. And you have a dt here. Okay, and so essentially, like QSSEP, this model is quadratic, and so you can write. I mean, all information in the density matrix is in the correlation matrix. Let me write down the correlation matrix. Is defined as this. Okay, and so C dagger J C I, and essentially, so you can write your time evolution equation, the one that you would write for the density matrix, you can write it for the correlation matrix, and you will get something of this sort. So this is already for the average over this noise of the correlation matrix. Some linear operator here acting on G average plus gamma G average, L gamma G average. You can actually proceed more generally and do the same for say cumulants of this G or moments of this G. So I take tensor product of R copies of this G, I average them, and I will get some L0 of R, G of R, tensor product R average, plus the same. Okay, and now, if you take the limit of this, in this equation, the limit gamma to infinity, and you rescale time appropriately with gamma, okay, then essentially what it means is that this term becomes much bigger than this. You can do perturbation theory if you want, and then since I'm taking these limits explicitly, you will get some effective dynamics happening on the kernel of this of this operator. And this effective dynamics is precisely that of QSEP. So this is how QSEP appeared. And okay, and let me just pause to a small note. You could actually, in the same way as we took the average of QSEP over there and we got SEP, you could actually take the average of this one. You would get tight binding model with dephasing. And I'm just going tight binding model plus dephasing. And if you do the same procedure here on this model and you take the limit gamma to infinity and you rescale time appropriately, you get SEP. Okay, which you should, because essentially what we are doing is just the average from QSEP, and I've just shown that the average of QSEP is SEP. Okay. Now, now I want to make a point here that essentially, in this case, so essentially in this case, when you're in this limit, essentially your evolution happens on the diagonal of your density matrix. Tight binding. Yeah, that no, yeah, these, just these, yeah, these plus dephasing. Okay, and so essentially, as the dynamics happen on the diagonal, here you should have classical fluctuations in this case, and in QSEP, which is on this case, essentially you have fluctuations on these off diagonal terms, and so you have fluctuations on incoherencies, and so I would call these quantum fluctuations. Which will bring us in some sense to the quantum MFT. Okay. And so, okay, so let's continue and looking at QSEP now. Okay, so what is this kernel? So this kernel of this operator is essentially, if you consider this object, so again, your moments, so I1, J1, IR, JR, and you take the average. Essentially, this kernel corresponds to when you have the i's, so the i's are on the left and the j's are on the right, and corresponds when the two sets coincide. So essentially what this means is that QSEP dynamics will occur on essentially on these, I mean, you can write it as on these objects where the I indices, so the left indices in these G's, are the same as the J indices. Okay, and I mean, you could, I came from this way, but you could have like seen it directly by considering the Hamiltonian of QSEP and shown this as well. And so essentially from these you can write all these objects in a diagrammatic way. So since you always have the same number, so if you have some index on the left, you must have some index on the right at some point because the sets must coincide. So essentially you can represent your vertex I1, and so it must have one leg being G leaving I1 and one other entering I1. So these would be the right index and these would be the left index. And okay, and then you can have I2 here and so on. In principle, you could have, I mean, now you can have connected or disconnected diagrams of this sort. And okay, maybe I should move there. What is I'm going to erase this. Okay, and eventually we are interested in the steady state of this, so taking the limit, taking the limit to infinity. And it happens that in these cases, once you also consider the thermodynamic limit, only connected diagrams are relevant. So essentially, your connected diagrams, if you take in the steady state, connected average of these diagrams, so essentially you have some index I1, 2, 3, so on, IN. Okay. These to scale, so these to scale as 1 over L of R minus 1, and all disconnected diagrams scale subleadingly to this. And so essentially, this means that the thermodynamic limit of this model is essentially dominated by these connected diagrams. Okay, and okay, in the thermodynamic limit, I would represent these as I1 equals some I1 over L equals x1, and so on. And so these would be some function of these indices. Okay. Questions? What do you mean? Okay, so okay, so these are essentially, so if you want, GII is the average density at site I. Essentially, these are, so then these are coherencies that will fluctuate, but then okay, so these are a certain specific set of coherencies that you have, that essentially you, yeah, okay, you have the same amount of, okay, essentially what you're computing here are specific averages of these expectation values of these coherencies. Yeah, okay, if you want, that's why, yeah. Yeah, essentially, if you want, everything is encoded in these type of objects for any R. And yeah, and I'm just looking at dynamics of these. Okay. So you mean a large deviation function for, so you could write something like, so, but this comes from descaling, so you could write so essentially, so this would be some sort of cumulative function for these G's, the correlators of G's, and you take derivatives with respect to this A matrix, and you would get. No, the average goes. Yes, the average goes inside into log. Okay, this would be some cumulative. Yeah, this would be some cumulative function for these correlators, because I mean, this scaling is, I mean, you have R vertices, you have L to the R minus 1. It's precisely the scaling that you would get from this. Okay. Now, okay, why this matters? No, wait. Okay, because now you can connect these type of objects with CEPs correlators. So essentially, if you want to compute, so remember that the average dynamics of this model is CEP, so that's where the relation comes from. So if you want to compute these type of object in CEP, this is the classical expectation value of densities at different sites. In the thermodynamic limit, this would be precisely this times these functions, but you need to sum, okay. You need to sum over all permutations of these indices, of these x's. And so essentially from this side you have the, I mean, density correlators of CEP, which would come out from, if you want, from macroscopic fluctuation theory in the thermodynamic limit. And on this side, we have these objects that come from fluctuations of these coherencies, the expectation value of these tensor products of G's. Okay, but in this case, there is more information in QSSEP if you want, because here we are averaging over all permutations. We are summing over all permutations to recover all information about CEP. But these functions, we don't know everything about them, because we just know, I mean, from CEP we just know about these sum over permutations. So if you want, there is more information in these QSSEP, and okay, and this would be okay. And here I could say that they encode these quantum fluctuations and information about this quantum macroscopic fluctuation theory. Okay, there is also, so these are the connection between the correlators of the density and QSSEP's expectation values of these coherencies. You could also talk about transport and ask if in the system you compute the cumulative rating function of the current, and you can show that the cumulative rating function of the current goes to CEP, goes to the same value of CEP. I mean, this is something that I did in a paper. And okay, and so additionally to this, the cumulative rating function of current at leading order, CGF of the current at leading order matches steps CGF, the one of QSSEP now, QSSEPs. Okay. No more questions? Okay. So essentially there is also, okay, a point from this side. So essentially here what we were doing is we were scaling, so taking limit gamma to infinity and scaling time appropriately and showing that these models, so these more quantum models, say this is a bit more of a quantum model with noise coupled to charge, goes to QSEP and so on. But we could ask, what if we don't take the limit, gamma to infinity, and we just consider these type of models at finite gamma? And instead we just simply take thermodynamic limit. And okay, essentially, this is just conjecture. Essentially what I would expect generally is that you could, so essentially we want thermodynamic limit, and you could argue by some RZ argument that as you take L to infinity, this parameter, the gamma, grows with L to infinity. And so effectively your theory is becoming the gamma to infinity limit, and it's becoming QSEP in the same way that I would expect in this case, this theory is becoming SEP in the thermodynamic limit by some RZ argument. People have also computed the Kuhlmann's rating function of the current here for this model, for type binding and dephasing, and they've shown that, so this is Nardis, 2014, I think, and also show that CGF of the current converges to that of SEP in thermodynamic limit. And so this would also, these at finite gamma, so at finite noise strength. So another argument for the fact that we would expect in thermodynamic limit this model to converge to SEP. Yeah, but this is still conjecture. I'm still working a bit on this side also to show that in the thermodynamic limit at finite gamma, you should expect this model to become essentially QSEPs in the thermodynamic limit. And these QSEPs in the thermodynamic limit would be what we call the quantum macroscopic fluctuation theory. In the same way that these in the thermodynamic limit is the macroscopic fluctuation theory for SEP. Yeah. So I would call, in this case, I would call the theory that would describe this QSEP in sort of the thermodynamic limit in the continuum, if you want. And it would have information about all these coherencies, which of course are quantum fluctuations, and they don't have a classical analog. Okay, you can relate them then to SEP's result, but something like, for instance, over those permutations, but there is more information here. So, okay, so wait, so from the SEP side, you have macroscopic fluctuation theory with which you can compute those. So essentially you have a path integral like theory, which is macroscopic fluctuation theory, from which you can compute those correlators of the density in thermodynamics. Yes, at points that are far away. Yes. In this one. Those, yeah, yeah, if you want, yes. Yes. Yeah, but yeah, okay, yes. So that's it. But these okay, but these things they really converge to that function even if they are like one side apart. I mean, if you take like, okay, that would be something like say nj plus 1, the 1, and k. These would be effectively the same as, okay, as the average in, I mean, in MFT language, as the average of rho x for this j, rho x squared, rho y. So what I'm saying is that, I mean, okay, you can intuitively think of these as if they are far away, but it's still valid that if they are one side apart, you still get the same thermodynamic limit. Like you get density at site j times density at site j plus 1. Yeah, even microscopically, this would converge in the limit out to infinity. These would converge the same function. Yeah, it would be the same as, yeah, as if they are far apart. Okay, yeah. Yeah. Yeah, but essentially that's what you're saying. Essentially, what we want is to compute, is to get some field theory that would describe these type of objects. Yeah, of course, in diffusive scaling limit, yes. And time with L squared, yes. Yeah. What in this so okay, so if you want, these objects are quantum in a sense, because I mean these are off diagonal components of G. The classical things live in the diagonal of G. They are these densities. So these are coherencies. So these objects are fully quantum. But it happens that because of these model, no, I can compute the sum over these permutations in CEP. I don't have access to this function. If I know CEP, I still don't know S. Because this is the sum of the permutations. There. And these happens to be these quantities happen to be connected because CEP is the average of this model. So I mean, okay, the difference between the two would be that MFT, normal MFT or CEP's MFT gives you, I mean, it's some path integral that gives you, like with some density and some current, that gives you those type of correlators. And these would give you these objects, these quantum coherences. What do you mean by from the point of view of current? Um, yeah, okay. I mean, from the point of view of the current, yeah, essentially what we've shown is that both of them coincide. And okay, I mean, of course. Okay, well, let me rephrase. Of course, these macroscopic these theories would be related, even because the average is the same. So they are related at the average level. But what I want to say is that this gives you more. This gives you access to these. I mean, this QMFT will give you more. It would give you access to these, which you don't have. Like it's not well defined in the classical macroscopic fluctuation theory. No. Mm-hmm. Mm-hmm. I know the path that maybe it is. It's not at least the way that we're thinking in. Oh, sorry. Uh-huh. Uh-huh. Yeah, maybe it could. I mean, I don't know. I didn't think in that. I mean, we're trying to take another approach to that, but maybe that could also work. Yes. Essentially, we're be trying to yeah, okay. Because you still need to I mean, when you go to write some quantum macroscopic fluctuation theory, you still need to get some current and some density fields from that. I don't know how I would do to get those from that approach. Um, yes, no, but okay, but still you can get your dynamics on these type of objects. Dynamic, this is still valid. And yeah, I think, I mean, you would need to, I mean, okay, of course, if you want to compute the R correlator, you would write the Liouvillean for the R replicated system, and then you would, I mean, I don't know, if you want to compute the average, like the time scale at which the system decays to the steady state, you could look at the gap of these Liouvillean. Yeah, okay, this would be something that you could do. It did, I mean, for the, okay, but I mean, the Liouvillean for this is, it's bigger, it's like L to the R. Yeah, but yes. Yeah, I actually wanted to study a bit that before I presented this, but I didn't have opportunity to. Yeah. So okay. I mean, okay, from I mean, there is these as you were discussing, there is these precumulants part of these that, I mean, I'm not sure if there are still like open directions there. I mean, there is these open direction of computing. I mean, these QMF, arriving at this effective field theory description for this QMFT, for this QSSEP in thermodynamic limit. There is also, if you want, so for instance, in the cumulative rating function, so these happens at the thermodynamic limit is both match. So essentially, the cumulative generating function of QSSEP is equal to that of SEP in the thermodynamic limit. But they are, of course, at order 1 over L squared. You have corrections that, and these two don't agree. And so in a sense, you would have information about quantum fluctuations in this leading term. And you could, try to analyze these. So these are things people are trying to investigate as well. So, okay, so SEP, if you, okay. So, okay, of course, here SEP appears in quantities that, I mean, a sum over quantities that are not diagonal in G. Yeah, of course, the densities are diagonal. So if you're looking at SEP's model and you look at essentially what is relevant for SEP's model is the diagonal of G, because you won't get off diagonal of G in SEP. Yeah, of course. But then, I mean, for QSEP, you have quantum fluctuations, and essentially, I mean, because of like the one model is the average of the other, you can relate these quantities in SEP, which would be sort of okay. These correlators with that. Yes. Yes. Yeah, you would see SEP. Okay, you would see SEP in something like this. So you if you took Gij, Ji, you would see the expectation value of these would actually match Ni and J. I mean, in this simple case, yes, because I mean it's trivial. Permutation is trivial, but for higher correlators, you can't exactly recover this function because I mean you get these permutations are relevant. So okay, so SEP's information is hidden in the quantum fluctuations of QSEP, if you want. But there is more information in these quantum fluctuations because, I mean, this is true here, but if you go to some, yeah, if you want some information of the classical SEP is hidden in these quantum fluctuations of these coherences in QSEP, like this. So in this case, I could recover. I know these in thermodynamic limit simply from knowing the SEP's results. For higher cumulants, that is not true, not necessarily true, but they are still related by this expression. Because I mean, it's this expression, right? You agree with this expression? Okay, it's literally now you have 2x, you have x1, x2. You need to sum over permutations, but I mean that you have x1, x2, and x2, x1. But that is, I mean, literally the same thing. Just writing Gij, Gji, or Gij. I mean, you can recover this relation from if you want, this comes from the fact that essentially in the end, all you're computing are moments of this thing. So these would be moments of, and taking the average of these. So you could put the average inside and you would get is equal to the average inside e to I, and I. And okay, this is SEP, right? And if you now take derivatives of with respect to AI, you get those cumulants. Okay, you put a log here. Here you could directly use some kind of Fick's theorem inside because the QSEP is quadratic, and you would put the average in the end, and so you'd get these correlators inside with the average in the end. So this is where that relation comes from.
Maybe it's a good time to close. Maybe it's a good time to close. Yeah. So let's thank João again.